Everybody, Mr. Smith here, shooting my 6th video of today. It's my last one. 2 days worth of video shot in 1 day. Gotta say I'm losing a bit of steam, but this should be a shorter video, and it's an interesting topic. So I am looking forward to doing with you guys, and talking about applications of centripetal force. So let's get started. So the first application we'll look at in a bit more detail is roller coaster design. So the first roller coasters built in the early 1900s had like circular loops. And honestly, if like I was designing a roller coaster without much knowledge, I'd be like, yeah, I mean, you make a circular loop. But to have the roller coasters safely traverse the loop, as we saw in a previous lesson, they have to be moving pretty fast, because they have to be moving fast enough so at the top they don't lose contact with the surface. And I know their wheels are kind of contained in tracks, but they have to be moving really fast here to go around the loop with enough speed to kind of safely move around. And with the circular loop, that speed was very fast. And I don't know if you can imagine a rickety old early 20th century thing moving very, very fast. Yeah, lots and lots of injuries. Today, roller coasters have a different design. So the radius starts off large and then gets tighter and tighter and tighter, and then gets larger again as you go out. And the shape is called a cloth-eyed loop. And it is more safe. But why is it more safe? So that's what we're going to analyze first. A little problem. So we're going to look at a scenario where the radius of the cloth-eyed loop, kind of at the top, is half the radius of a circular loop. So we'll call R1 the big circular loop, R2 the radius of the cloth-eyed loop. And so the first radius is twice the second radius. And we're going to compare, so how fast a roller coaster car must be traveling to experience a normal force twice the force of gravity at the top of the loop. So that means this. So I think we've all been, if you haven't been on a roller coaster, maybe you've been in a car that's turning fast. But whether you get pushed to the side of your car, or you're in a roller coaster and you kind of come out of your seat or get squashed into your seat, that kind of is what makes the ride fun. And that force we feel from the whatever we're sitting on is that normal force. It kind of provides the fun, makes us feel a little uncomfortable. And here we want that normal force to be experienced to be twice the force of gravity. So we're going to set Fn to be 2 mg. It's like we're experiencing 2 Gs of force. It's like, if the normal force is like twice the force of gravity, think about right now, sitting in your chair or what have you. Myself, I'm around 80 kilograms. If I were to feel a normal force equivalent to twice the force of gravity, sitting in my chair, I would actually feel like I weigh twice that, like I weigh 160 kilograms. And if you're not used to that, that can be quite the shocking feeling. But again, that's kind of the fun of roller coasters, for you to briefly feel that. So let's talk about what's happening. So at the top of the roller coaster, and no matter what, this is the free body diagram, no matter what the roller coaster looks like, whether it's a circular loop or a cloth-eyed loop. So you have your cart, and you've got gravity pulling your cart down, and then the cart is in contact with the surface, and we are saying that normal force, that contact force, is equal to twice the force of gravity. And our centripetal acceleration is down towards the center of the motion. So let's analyze this with Newton's second law. And we're going to get an expression for the speed necessary to experience that force. So sum of forces equals mass times centripetal acceleration. And here we have the gravity plus the normal force, which we said is 2 times the force of gravity. And notice we get, those are like terms. So we can add those together and get 3 times mg equals mass times acceleration. And if you notice that no masses were given in the question, and you know what I actually want to, what I've been doing in other problems is because this is a problem involving speed. I've often been subbing in speed right away for our AC. So we are doing a speed problem, mv squared over r, mv squared over r. And again, yeah, you'll notice we don't have the mass. So this speed for roller coaster makes anyone, regardless of their mass, experience this normal force of twice the force of gravity. And if we solve for v, we are multiplying up the r. So we get 3 times g times r. That's v squared, and we'll have to square root. So an expression for the speed required to experience twice the force of gravity as the normal force, feel twice as heavy, is root 3gr. So let's make use of that. Now we're going to compare. So we're going to compare the ratio of speeds to the two designs. So we're going to look at a ratio of the speed with the new coaster design to the speed of the old coaster design. So the speed of the new coaster design would be the root of 3 times g times r2, right? R2 is the radius of the new roller coaster design. The old roller coaster design had a radius of twice that radius. So 3 times g times 2r2. And if we look at that, we have a lot of things being divided out here. 3's divide out, the g's divide out, the r2's divide out, and what you're left with is the root of altogether 1 over 2. And if you try that yourself, do 1 divided by 2 and take the square root, you get about 0.7. So what this means is, if I can write this another way, is that the new speed is 0.7 times the old speed, or 70% of the old speed. So to experience the same Fn equals 2 mg, which I'll just call, like in general, to experience the same thrill of ride, right? The new coaster only has to go 70% as fast. And, coming down from 100 kilometers per hour to 70 kilometers per hour can make a big difference in terms of energy. You don't need as high of a roller coaster to achieve those speeds. It just makes things safer for everybody. So yeah, a pretty interesting problem that we can apply this idea of uniform circular motion and centripetal force to talk about the design of roller coasters. So that's pretty fun. The last thing we'll talk about in this lesson is centrifugal forces and an application of that. So last unit, we talked about frames of reference. In each case, in our last unit, we were talking about inertial frames of reference. So this is a frame of reference in which the law of inertia is valid. So Newton's first law. So the law of inertia was, basically things at rest will stay at rest unless there's some external force. And things in motion will want to stay in motion unless there's some external force. And for the case of, a car driving by at some constant speed, just in a straight line, or in somebody just on the roadside looking at it, those were two inertial frames of reference. But when an object is in circular motion, it's accelerating. So any motion observed, if you're in that object, will exhibit properties of a non-inertial frame of reference. This is a frame of reference in which the law of inertia is not valid. So we're going to hopefully clarify that for you, if that's a little fuzzy right now, with an example. So think about if you are the passenger in a car, and the car is doing a left-hand turn. So hopefully most of us have experienced that when the car turns sharply to the left, you kind of feel that you're kind of moving to the right and you're pushed against the side of the car. You feel as if your right shoulder is being pushed against that passenger side door. So we're going to look at from two different frames of reference. So for now, we're going to look at it from an outside observer. So from the Earth's frame of reference. So maybe you're in an airplane, just like, or a helicopter hovering above this and looking top down, or on the side of the road. It doesn't really matter. But let's draw a free body diagram for this one, and then just have a little bit of a team talk about it. Okay, so I'm just drawing a free body diagram. So that's my person in the car. And I'm actually, you know what? I might actually draw, I'm gonna try to draw, I'm gonna go out of my comfort zone here. I'm gonna try to draw a bit more of a better car. I'm gonna draw the front view of a car. So here's the bumper, here's the car with the windshield, here's a tire, and here's another tire. Okay, and let's actually make this the back of the car. So here's the license plate. All right, that's pretty good, I'd say. What forces are acting? Let's talk about the person. We're looking at the person inside the car. What forces are acting on the person? Well, we have gravity going down. We have a contact force. The car's surface pushing up on the passenger, Fn. And from our perspective, the person in the car is traveling in a circle, right? That their path is just a uniform circular motion, and the thing providing the centripetal force for the person, the thing forcing that person towards the center of the curve, is the force of the door on the passenger. And the acceleration is this way. And I'll just call this, what did I call this in my notes earlier? I'm going to call this Fn comma door, because it is like a normal force. It's a surface contact, but they're in contact with the door as well. So yeah, the door is just providing the centripetal force. So, there's nothing really crazy is going on. We're not Newton's first law isn't being violated here. That person is experiencing a net force. That force of the door on them is causing them to move in uniform circular motion. So from Earth's frame of reference, they see the passenger traveling in a circle, and the normal force from the door is the centripetal force. So nothing crazy. So this is the Earth's frame of reference is an inertial frame of reference. So nothing fuzzy here. Newton's first law is holding. So this is an inertial frame of reference. But now let's consider what happens when you're the passenger. So try to draw my fancy car again. Bumper, license plates, car body, car window, tire 1, tire 2, person in the car. So this is from the passenger's frame of reference. So for the passenger, they have gravity, the normal force from the floor. But let's think about this. The passenger in the car, the passenger doesn't experience themselves. They're not flying through the driver's side window or flying through their passenger side window. They're just in their car seat. They're not moving. They're not moving in their car seat. So for their perspective, the net force on them must be 0. So yes, they have this force of the door on them. So Fn door. But if they're not moving, they must be kind of experiencing some other force to keep their net force being 0. And this is what we call this centrifugal force. So because the passenger is stationary in their frame of reference, the sum of forces must be 0. And what they feel is this fictitious centrifugal force. So we actually know there's no there's no real force acting on the person, but because their frame of reference is accelerating, something must be going on. That's why we move. That's why this person would be moving to the right, because they are moving in a circle in their car. But as far as they're concerned in the car, like they're in their seat. They're not accelerating. So if the door is pushing on them, they're gonna feel themselves pushed against the door, and they're gonna kind of lean to the right. A practical application of the centrifugal forces is a centrifuge. So if you think about when a car starts to turn, what happens to you? Just like we've talked about, you kind of lean towards the outside of your car, right? The same thing happens with a centrifuge. As maybe a beaker is rotated round and round and round and round. Well, if you were a particle of something, or a blood cell, or a special type of blood cell, you would move towards kind of the outside of your test tube as well. A centrifuge is a rapidly rotating device used for separating substances. So centrifuges are used to separate, blood platelets and white blood cells and red blood cells in a blood sample. As you spin maybe a test tube of blood round and round and round, the certain large types of cells would settle to the bottom, and then you'd have the different next type of cell, and it kind of separates them out. The same thing is used to remove debris from water and like filtration systems. Centrifuges are used a lot. And again, the idea is, so a particle here, as the centrifuge rotates the tube round and round, that particle is just going to keep drifting and drifting and drifting to the outside, essentially settling on the bottom. And you can kind of separate particles out of a liquid, which is pretty cool. A little short note here. So as the centrifuge rotates, a particle at position A, excuse me, will tend to continue in a straight line. And again, just kind of drift and drift and drift until it reaches the bottom, and in this case, in the test tube, it settles at the bottom. So a pretty cool application of these non-inertial frames of reference is using the centrifuges. So that's pretty cool. All right, guys. So up next, we're going to take a pause on uniform circular motion. We've actually learned basically all we need to about uniform circular motion. We're going to learn about Newton's law of gravitation. What is the equation governing the attractive force between two objects? Afterwards, we'll take that that quantification of Newton's law of gravity and use that as our centripetal force to begin to analyze things like the planets, moons, and satellites. It'll be a lot of fun. All right, guys, I can feel my voice is going. Got my 6th lesson in the books for today. Hope you guys are staying well, and we'll see you soon.